Hello everyone, in this video I'll be explaining the solutions to each problem of Biweekly Contest 57. So yeah, let's get right into the first problem. So in this problem, you're given a string and you want to make sure that every character inside the string occurs the same number of times. So in this problem, you just need to maintain a count of each, how many times each character occurs. So I have initialized an integer array, and I have 26 spots in the integer array, and each spot will correspond to how many occurrences of that letter there are. So I go through every character and I add 1 to its corresponding index. So if an A occurs, I will add 1 to the first spot of this array, and B, I'll add 1 to the second spot, etc. Then I just check that all the counts are the same. So I go through each number I have in my count, and so this is the number of characters that there are. So if I haven't run into one yet and I see a count that's greater than 0, then I set that equal to what we're checking, and otherwise I just check that the count of that character is equal to the count of our previous character. So this will just check that each character will occur the same number of times. So if we submit this, it gets accepted. And now let's move on to question 2. So in this question, you are given an array of times, and each time represents the time when a person will arrive and the time when a person will leave. So in this example, person 0 will, friend 0 will arrive at time 1 and leave at time 4. When a person arrives, they will take the lowest numbered chair, and you're supposed to return the chair number that your target friend will sit on. So in this example, you're supposed to return 1 because this friend here will come in and sit on chair 1, as chair 0 is already occupied by this person. So in this problem, I just kind of simulated it. So yeah, I'll explain the idea behind the solution first, and then talk into how the code is actually implemented. So the idea is that if we sort the array of times, like what was it? Let's just copy this one. If we sort the array of times by the start time, so we'd want this guy first, 1, 5, then this guy second, 2, 6, and then 3, 10. If we sort it by the start times, then what we can do is we can just simulate it, because we know this person will arrive first, and this person will take a chair, and then this guy, when he then we'll have a priority queue, which represents when everyone will leave. So we know this guy will come in first and take chair 0, and he'll leave at time 5. So our priority queue here will have 5 in it. And then this guy will come in and he'll take chair 1, and our priority queue will have 6, and then etc. And let's say another person came in and they came in at time 5. Then we know that this chair will be free because this person leaves at time 5. So we can assign chair number 0, because this person took chair number 0, to this new person. So that's the idea. So let's look at how that's implemented. So first I made a helper class, which just tracks the index of each person in this array, because we want to return the answer, the index that matches the target friend. And once we sort this thing, the indexes might get messed up, so I just save that in a field. So I make a new array and I just copy the information over. And I sort the array based on the arrival time of each friend, which is this. Then I have a priority queue of chairs that are available. And yeah. And then this is the priority queue representing when a person will leave. So now I go through everybody in the list. And so this loop here, what this does is it looks at the people who are next to leave. So let's just say the next to leave person is at time 3. And it looks at this person's arrival time. And if the next person is going to leave before or during the time that this person arrives, we can remove them and add their chair back into the list of chairs. So this list of chairs will just be the next chair that we will assign to a person. And so let's look at this case first. So this is a general case. So if we don't have any chairs that people left, then we know that the next chair will just simply be the size of how many people are at the party. Because let's just say there's one person already sitting in a chair at the party, then you pq.size will be 1, and we will make a new class here that represents that the next person who comes in will take chair 1, and they will leave at time I.t, the first index, because yeah, we're just looping through the helpers. And otherwise, then we know that somebody left their chair, so we will just take that from the list of chairs that people left. And then what we can do is when we find the person that is our friend, we can just return that the chair they're going to sit in. So if there are no chairs in our list of chairs that people left, then we will just say that they'll sit in the next available chair. Otherwise, we know that there are some chairs that people, somebody came to the party, sat on chair 0, let's just say, then they left, and now chair 0 is open for other people. If it is, then we will return that. So this kind of simulation is accepted, and it works because if you notice, the length of this array is less than 10 to the 4. So sorting this is nlogn, and maintaining these priority queues is log n, and this is n. So this for loop will also be nlogn. So yeah, whenever you see this 10 to the 4 or 10 to the 5, usually there's a nlogn solution. So yeah, so for this problem, you just simulate it and return the chair that your friend sits in. So let me just clear this. Now let's talk about question 3. And this problem, I actually just mind blanked. I spent like an hour on this problem, which I definitely should not have, because it is actually pretty easy. But I was just using the completely wrong approach at first. So in this problem, you're given these segments that are to be painted with a color. So what this means is that the segment from 1 to 4, so 1 to 4, will be painted with the color 5. And then the segment from 4 to 7 will be painted with the color 7. And the segment from 1 to 7 will be painted with the color 9. Then you're supposed to return a list of these triplets where each one just represents a different color on the finished painting, right? So, and each color is the sum of whatever paint was applied. So that might be a bit confusing, so I will just explain what I mean by drawing it in this. So after all these paints are applied, the segment from 1 to 4 will have the color 5 plus 9, which equals 14. And the segment from here to here, 4 to 7, will have the color 7 plus 9, which equals 16. So then you're supposed to return 1 to 4 with the color 14, and 4 to 7 with the color of 16. And similarly for this one, you want to break it up so each different color will have its different segment. So in this example, 1 through 6 will have the color 9 because only this thing will be painted. Between 6 and 7, the color 9 and the color 15 will be painted, so you sum those, and etc. So now that we know what the problem's actually talking about, we can get into the solution. So this is actually a pretty common kind of problem that I just totally blanked on the solution for, even though I've done these before. So the idea is that you can place a flag indicating, so first of all, I'll talk about the brute force solution. So as you can see, we can imagine this number line here as like a number line, right? So you can start at any number and end at 10 to the 5, and there will be 10 to the 4 segments. So ideally what we want to do is, if we know that we paint from, let's say, here to here, we can go for loop, go through here, and for every color, every number in here, we can just add the color that we paint. So if we paint this segment with 1s, we can write this, and then if we paint this segment with 2s, we can just add 2 to each of these numbers, and etc. But this doesn't work because in the worst case, when all your segments start at 1 and end at 10 to the 5, you will have a massive, your runtime will be way too long, because for every segment, you are going from 1 to 10 to the 5. That's n squared, which doesn't work because n is simply too large. It's 2 times 10 to the 4 times 10 to the 5. But a simple workaround around this is that you can just place a flag at the start of your thing and at the end. So let's just say we want to fill this entire thing with 1s. We can simply place a flag saying that when we enter this number on the number line, we add 1 to our color, and when we exit, we subtract 1 from our color. Then we can just do that for each of the segments, and that will just be all of n time because we aren't looping through here. And then at the very end, we can loop through and use these flags to change our color. So for example, if we color from here to here with the color 1, then we will set these flags, and then if we color from here to here with the color 2, we'll set these flags. Then at the end, we can simply loop through just one time and maintain a color. So if our color starts at 0, we'll know that this will be 0. This adds 1 to our color, so color will be 1, color will be 1. This adds 2 to the color, so color will be 3. And then this subtracts 1, so color will be 2, and then etc. And as you can see, this will return the same result because it's just like sorry, let me just erase this. It's just like that we first filled in this segment with all 1s, then we added 2 to each of the elements here. So we added, so if 2 starts from here, we'll add 2 here. So then this will be 1 plus 2, that's 3, and then we'll fill it in. And instead of having to loop through this one and then this one multiple times and adding it, we can just place these flags and at the end do one loop, and now we've done the entire thing in O of n time instead of O of n squared. And that's pretty much the solution. So if I just erase this, now we can look at how the solution is implemented. So here's the array where I placed the flags, and this is not needed. That was just a failed idea I had. And here we will place the flags. So this is the starting index, so we'll add that color there. And this is the ending index, so we'll subtract that color there. So we are just placing a flag at the starting index, which let's say adds the color 3 and or whatever, because this is the color S2 right there. And then we will just loop through that one thing one time. And I'll explain this Boolean array later. And we will just keep the previous index of when this current color started, and we will go through. And so essentially, if we this is where we place the flags. Let's just this is the Boolean array, and if we place the flag there and the color is not equal to 0, so that means let's say color is 3, then we go along, we find another flag, let's say the start of another segment, 4, then we know that we want to return a segment where this will have color 3s, right? So we will add the previous, and then the current index, and then the color, which this segment was painted, and then add that to our answer. And otherwise, if the color is 0, so let's say there's a bunch of zeros, and then we find a color here, 4, then we know that we will set the previous to that index and the color to this. So then the next time we find a thing, let's say -4, or when the segment ends, then this will be tracked because we placed a flag here of -4, and then we'll go from here, this segment, to here, and say that that was all painted with the color 4, which is what we do here. And the reason why we have to use a Boolean array here is because of this third test case here. So if you notice, 5 plus 7 is 12. That means that this first 1 through 4 is painted with 12, but 4 through 7 is painted with 1 plus 11. That's also 12. So when you're placing the flags, you will end up subtracting. You'll place a -5 here at 4 and a -7 at 4, but you also place a +1 and a +11 at 4. So 4 will be 0. So you will pretend like there's one big segment from 1 through 7 with the color of 12. However, in their problem, they want you to split these up because the mixed color sets are different, so it is not one single segment. So just because the color doesn't change, the color of this is 12 and the color of this is 12, because the sets are different, because this 12 is made with 1 plus 11, this is made with 5 plus 7, you still want to split them up. And so we can just split them up by placing a flag here. And this is a possible workaround because each color is distinct. So we know we will never have a 5 and a 7 and then another 5 and a 7. So every time we make a color, that is a unique mixed color set. So every time we place a flag, that will be a segment that we need to return. And if we submit this, it gets accepted. Yeah, it gets accepted. And yeah, this is just a classic workaround to this sort of 1D number line problem, where instead of looping through and filling in the color, you can place flags starting for the start and end point, and then go through at the end with one loop. And the main observation here is that each color is distinct. So even if we have a flag of 0, as long as we change stuff there, then we know we want to make a new segment with that. And now let's go into problem 4. And the sad thing is about this contest is that I took so long on question 3 that I only had like 15 minutes left for question 4. And I ended up finishing it right after the contest ended, which is quite unfortunate, because if I actually had a brain for question 3, I think I could have easily finished question 4 inside the allotted time and solved all 4 questions. So yeah, let's just explain this question. So in this problem, you are given an array of how tall people are. So this would represent that at the first index, there's a person of height 10, and then a person of height 6, then 8, and etc. And you are supposed to return an array where that represents how many people each person can see to the right of them. The definition of if somebody can see somebody to the right of them is if everyone in between those two people is shorter. So if we look at this person, height's the first person, we know that they can see 6 because everyone in between 10 and 6, there's nobody. So everyone's shorter technically because there's nobody in between them. For this person, 10 can also see 8 because 6 is in between them, but 6 is shorter than both of them. But for 5, we see that there's 2 people in between them that are both taller. So this person cannot see this person because everybody, for them to be seen, for this person to see this person, everyone in between them must be shorter than both of them. But since these people are taller than this person, they can't see it. And etc. for every person. So if we look at this, we know that there are 10 to the 5 people. So a brute force approach will not work, and we need to come up with a more clever way to approach the problem. So the first observation here to make is that once a person sees a person that is just as tall or taller than them, they cannot see any more people. Because, for example, if we have a person this tall and a person this tall, they're the same height, then we have a person taller. This person here cannot see this person because, as we see in their requirements, everybody in between has to be shorter than both of them. So anybody after here, taller, shorter, doesn't matter. If we look at everybody in between, they have to be shorter than both of them. But because this person is in between, and this person is not shorter than this person cannot see any more people after this person, no matter how tall they are. So that's the first observation. And the next one is that, let's say we have a person that's this tall and a person that's this tall and a person that's this tall. So each person can only be seen by the person just to the left of them that is taller. So if we look at this example, we know that this person can be seen by this person, but this person cannot be seen by this person because this person in between is taller. So each person can be seen by the person that is just to the left of them that is taller or just as tall as them. And so using this, what we can do is we can maintain a stack of the heights of people starting from left to right. And then what we can do is every time we add somebody to the stack, every time we go look at a new person, if they are shorter than the person in the front of the stack. So first we will add this person to the stack. When we add this person, if they are shorter, then we know that this person can see this person. So we will, in our answer array, we will add 1 to the number of people this person can see. And then we will add this person into our queue, our stack. And we do that with the same for this one. So then we see that this person, when we move on, we check this person, and we see that this person is in our stack. So this person can see this person, so we'll add 1 to the second one. And now we just need to check once we find a person that's like taller, right? So that means that this person cannot see anybody after this person. So that means after we run into a person which is taller than the front person in our stack, this person cannot see any more people. So we can just remove them from the stack because we'll never need to use them again. And we will add this person to the number of people they can see. So we'll know that this person, no matter what the rest of the array looks like, can only see this one person. And then we will go to the next person, and we see that they're the same height as well. So we can just add 1 to this one, and we see that this person can see this person and this person, but no matter what the rest of the array looks like, they'll be stuck being able to see only these 2 people. But so we'll add 1 to this one. So we know this second person can see 2 people. This third person can see 1 person. But this first person, this person is still shorter, so we'll add 1. But we won't remove them from the stack because we know that if another person comes up, this person can still see them if this person is taller than everyone in between. So using this method, now we can just repeat that for every new person that we add, and we push them into our stack, right? So whenever we push a person into the stack, we know that if we push in a person shorter, that person can only be seen by the person that's just to the left of them that's taller. So if our stack has these 2 people, and we see a guy shorter than this person, we just want to add 1 to the number of people this guy can see. And because this guy is just to the left, and because we start from the left and go to the right, our stack will prioritize the people that are just to the left, right? Because the people that are more to the left will be further down in the stack. And yeah, so this basically combines the first 2 observations that we made. So then we will get the right answer because we will increment how many people the person just to the left can see. And whenever we see a person that's taller, then we remove these people from the stack, so we'll never increment them again. And this is exactly what we want to do. So if we look at how the code is implemented, so we will have an array which keeps track of our answer, and a stack which keeps track of the people that can still see somebody. So a person can still see somebody if there is no one that is just as tall as them to the right of them. And so for every person, while there are still people looking, and this person that is in the stack, that this is how tall they are, right? While they are less than or equal to this current person, we remove them from the stack, but we add 1 to the number they can see. So this is the case where, let's say we have this person in the stack, we run across a person that's taller. We know that this person can see this person, so they'll see 1 more person, so they'll see 1 more person. But they can't see any more people no matter what. So then we'll remove them from the stack. And this stack sort of represents the people that can still see someone new. And so if there are still people that can see someone, so let's just say we have a person in here and we added a person that's shorter, then we won't remove this guy because this guy can still see people. But we know that this guy is the guy that's just to the left that's still taller, so he sees one more person. So we increment that by 1. And we don't care if there's more people that can still see, because even though because this person can never see this person, since this person is in between them and taller than this person, the second person. So if there's a person that can see this person that we are currently adding to the stack, we will say that they can see one more person, but we won't remove them because this person is just taller than this person and they're just to the left. They're the first person taller than them on the left-hand side. And then we'll add our current person into the stack because now this person can potentially see a new person if they are shorter. And then we go to the next person, because this loops through every person in our array of people's heights. And we do the same logic. So now this person can see something. And if we have a guy that's even shorter, then we'll just say this person can see one more, because this person is just to the left and they're taller. But if this person's taller, then we still increment this by 1, but now we remove this person because this person cannot see any more people. So after using this logic for every person in our array of people, we will have how many people each person can see to the right of them, because we followed this logic, which stems from the first 2 observations that we made. So yeah. So if we submit this, it gets accepted. And yeah, so the crucial observation here is that whenever we add a new person, for all the people to the left of it that are shorter than him, they can see him, but they cannot see any more people. So we remove them from the people that can see another person. And this person who's taller, who's to the left and just taller, can see this new person and can still maybe see another person. So we don't remove them, but we keep now these 3 people who can see people. And yeah, so that's the solution to the 4 problems in Biweekly Contest 57. And yeah, as you can see, I took way too long doing question 3 because I just mind blanked. But yeah, so that's about it for this video. I hope you guys enjoyed it, and thank you very much for watching.